Hello, and welcome to this overview of how to analyze the frequency following responses with the Intelligent Hearing System's SmartEP. A 40 millisecond DAW is acquired to obtain timing information. Let's take a look at the typical characteristics of the auditory evoked potential to a 40 millisecond DAW complex stimuli, as described by Sko and Krauss. The stimulus is delivered at time 0, but there is a neural lag or delay before the response occurs. The stimulus shown on the top panel is thus shifted in this image to compensate for the delay shift and to demonstrate how the stimulus lines up with the response. Now analyzing the response, the front end portion of the response, which is a direct result of the onset of the stimulus, specifically the consonant simulation, which produces a transient response with a peak 5 of the ABR, is followed by a trough A, or the SN10 response. Then, you have the sustained portion of the aperiodical stimulus envelope with troughs C, D, E, and F, and finally, the offset of the stimulus, trough O. The timing latencies are typically marked for evaluation. The vowel portion of the stimuli, especially in the longer duration speech syllables, will produce a steady-state response that follows the transient and sustained responses. The FFR response reflects the acoustical characteristics of the stimulus used to acquire the response. The fidelity of the response to stimulus relationship is high in brains that can process the stimulus precisely. In panel A, you see on the left side the stimulus ah represented in the time domain. Next to it, to the right, you see the brain's time domain response to the ah stimulus. As you can see, the response shows similar characteristics to the stimulus. When you apply an FFT and convert these to the frequency spectrum, as shown in panel B, you also see very similar spectrums. When you run a time frequency analysis, as shown in panel C, again, you can see the similarities between the stimulus and response. FFT response waveforms have been converted to sound waves. When these files are played back, they sound very similar to the original stimulus that evoked them. In this slide, we see an image taken from the Objective Biological Measures for Assessment and Management of Auditory Processing Disorder by Drs. Jane Hornickel and Dr. Nina Krauss. In panel A, the DAW stimulus is shifted in time to reflect the neural conduction lag. In panel B, we see the FFR, which visually mimics the waveform of the stimulus in absolute timing and periodicity. Segmenting a portion of the FFR response, 80 milliseconds to 120 milliseconds, we can zoom in and measure the strength and magnitude of the pitch and harmonics from the frequency spectrum. Thus, FFRs provide a wealth of information. There's timing information, peak latency of the consonant and transient portion of the response in quiet and in noise. You can measure the accuracy, stability, consistency, repeatability of responses using cross-correlation and other measures. Cross-correlation measures can be applied to different portions of the responses, both transient and steady-state portions. You can also compare the response to stimulus and obtain a cross-correlation measure for this. You can also compare two responses to each other and obtain cross-correlation measures to them. Researchers acquiring using the block averaging feature can obtain FSP and FMP values. You can also monitor neural signature stability or fidelity through time. The FFR is different for each person but should remain consistent through time. Thus, monitoring for changes or differences in time can provide beneficial information. The cABR FFR analysis screen also offers a fast Fourier transfer, or FFT, of the response, where the response is converted from the time domain to the frequency domain. This FFT provides frequency and magnitude or strength information for the fundamental frequency and harmonics. You can also obtain pitch tracking, periodicity, pitch strength, and pitch error information. Phaseogram information can also be obtained. This provides timing difference insight between the transient portion versus the steady state portion of the response. And finally, spectrograms provide time frequency distribution of response, noise, and signal-to-noise ratio. Here is a sample 40 millisecond DAW acquired at 80 dB SPL. 3 runs of 2048 sweeps were acquired. Let's begin by calculating a grand average. Click on the process menu and make sure the addition mode is set to sweep weighted. Then press your Control key on your keyboard and select each recording you wish to sum. Once all 3 have been selected, select the Shift key and the plus key to sum. The new bolded recording is the grand average and can be moved up on the screen with the up arrow key or by clicking and dragging the recording upwards. Repeat the same selection process for the left ear recordings. And another way to add the recording is to return to the process menu and choose Add Selected Recordings. As you can see on the recording information panel, these are new recordings that have not been saved or assigned a file name. You can view the number of sweeps of the new recording, and you will see that the sum is now 6,144 sweeps. You can also click on the General tab and see the comment of the recordings that were summed. At this point, you can save the grand average recordings via the recording menu and Save Active Recording option. You can also add a text label to the screen that says Grand Average as you build your report. If you wish to continue processing the grand average waveform without saving it, you can do so as well. Researchers typically apply either a 70 Hz to 2000 Hz or a 100 Hz to 1500 Hz bandpass filter to the grand average waveform, and this can be done prior to saving the final waveform. For the purpose of this video, I will save the grand average waveform for each ear and then duplicate, filter, and save a new filtered grand average response separately. To duplicate the grand average recording, click on the recording to make it active, and then select the process menu and choose Duplicate Active to New Recording. Move the duplicates up on the page. Next, select the process menu again and choose Filter and then Filter Type. Select the spectral bandpass and enter 70 for the high pass and 2000 for the low pass. Click OK to register the filter change. Ensure that the duplicated grand average is selected, and then click on the filter icon on the toolbox to apply the filter to the active recording. Then select the duplicated grand average for the other ear and apply the filter again. As you can see, these new process recordings have not been saved and do not have a file name. You will see in the comments section of the recording that the spectral filter has been applied. Let's add a text label on the screen that reads Filtered 70 Hz to 2000 Hz for clarity, and then save each newly processed waveform. To save, select Recordings and then Save Active Recording. I will repeat the duplication of the raw grand average recordings process in order to apply a different and more narrow bandpass of 100 Hz to 1500 Hz. This filter bandpass will provide the clearest data for labeling because it is more limited and removes all frequencies below 100 Hz and all frequencies above 1500 Hz. Let's add a text label on the screen that reads Filtered 100 Hz to 1500 Hz for clarity. You can label this recording by hovering over peak 5 and right-clicking and selecting Mark Other Peak and choosing the ABR Peak 5 marker. This will place the latency marker. Click and drag the upward pointing amplitude marker to the negative trough valley. Then select the A label and click at the valley of the A. Do the same for C, D, E, F, and O. You can use your mouse and the time indicator available in the information bar to view the latency prior to marking the peaks. Once all the peaks are labeled, you will see the peak information in the Recording Information panel under the Peaks tab. If you wish to do an interoral comparison of these recordings, you can select a recording and press your Control key to select the other recording and view the Compare tab in the Recording Information panel. You can add that information to the page as well. If you are interested in timing differences between peaks, you can turn on the cursors and measure these differences as shown here between peak 5 and trough A. Now let's explore the longer duration complex stimuli. In particular, we're going to focus on the 170 millisecond BA and GA. Once again, there is a wealth of information that you can gather from these recordings. As with the shorter 40 millisecond DA stimulus, you can use either the raw grand average or the filtered grand average responses, but you should be consistent in your interpretation of data. For the transient response analysis, you can also obtain peak latency and amplitude, as well as latency differences from the time domain response. Here, you can see the responses to the three different stimuli: the consonant portion of the BA, a low-frequency stimulus, the DA, a mid-frequency stimulus, and a GA, a high-frequency stimulus, have different frequency composition that result in the different latencies of the early components of the cABR FFR response. As the response enters into the vowel component, the latency of the responses merge together. You can compare two recordings by selecting each recording with your mouse as you hold down the Control key. Then access the Rec Info button, which displays all the recording parameters and information for the active recording. Click on the Compare tab to show a comparison of all response peaks for the two selected recordings. IHS offers the following objective response measurements: signal-to-noise ratio, residual noise, and cross-correlation. FSP and FMP values measured over a 21-point range as defined by the midpoint in the averaging menu can also be obtained when block averaging was activated for your recording. These values are calculated over a user-defined range that can be specified manually or using cursors in the Response tab of the Recording Information window. Cross-correlation is a measure of the repeatability over a range of time. The cross-correlation can be measured for the response to itself when within active recording is chosen, using a split sweep calculation, or between two selected recordings. If you choose to obtain a cross-correlation of the active recording to all other recordings on the page, then a text file will be generated with the information. You can save the text file for offline analysis or copy and paste the information into the text editor tool to add the information to your report. Here we see the cross-correlation value for the 15 millisecond to 60 millisecond transient portion of the BA response. Here we see the cross-correlation value for the 15 millisecond to 60 millisecond transient portion of the GA response. Here we see the cross-correlation value for the 15 millisecond to 60 millisecond transient portion of the BA as compared to the GA response. The same measures can be recalculated for the 60 milliseconds to 150 millisecond steady-state portion of the responses. In this example is the BA response. Now we move to the additional cABR FFR analysis options found in the cABR FFR menu. We will begin with the General Analysis window. Here you will find two main pieces of information: the Fourier analysis for the frequency domain representation of the response, and the cross-correlation information for the stimulus-to-response relationship. As depicted in the right side image by Krause and Sko, a low-pass narrowband filter is typically applied for this analysis. The features of this module include the plot of the stimulus signal with access to the stimulus spectrogram, filtered and unfiltered, user-defined selection of the stimulus start and end analysis region for cross-correlation measures, cross-correlation stimulus-to-response function graph and table, selection of the stimulus and response high-pass and low-pass filter settings, which can be linked and saved, the plot of the FFR response signal, optional overlapping stimulus signal on response, response power frequency spectrum for the fundamental frequency and harmonic format magnitude and strength analysis, response phaseogram for phase information, response spectrogram, and export utilities. Here is a representation of the unfiltered response to stimulus analysis, while here is a representation of the filtered response to stimulus analysis screen. Let's take a closer look at the cABR analysis module. Activate the recording of interest and then select Analyze Select Recording from the cABR FFR menu. Click on the Stimulus menu and enter the filter bandpass of interest. For this example, we will use 70 Hz to 300 Hz to filter the stimulus. Your stimulus to response comparison should use the same filter bandpass. Thus click on the Response menu and set the same filter bandpass for your response. The filters are applied automatically. Next, set your stimulus analysis region. We will be analyzing the steady-state portion of the response, and for this example, we will enter 60 millisecond as the start of the analysis region and 150 millisecond as the end of the region. You can use the cursors as well. If you will use a certain bandpass for a specific stimulus to response comparison all the time, then I suggest you click on the Settings menu and choose the Save Default Filter option to permanently link these user preferences to your analysis. Users can examine the cross-correlation table and look for data points of high correlation. To activate the table, click on the display and select Cross-Correlation Table. Users can also align the stimulus with the response to obtain the highest R value. Note that the cross-correlation values are higher as the stimulus analysis region becomes narrower to several periods of the vowel portion of these stimuli. The absolute number of where this occurs is going to vary with different stimuli and potentially with different subjects, such as if there is a dysfunction-based latency delay in a particular subject. Over to the left, you will see the frequency spectrum with the fundamental frequency and the harmonics. You can move the frequency selection vertical bar to obtain magnitude strength microvolt information for different frequencies. In the center, you have a phasor plot representing the frequency selected. IHS offers several export functions. From the cABR FFR analysis module, you can export the cross-correlation function and the power spectrum to a file or to the clipboard for easy pasting into Excel and other programs. You can also save recordings to ASCII. You can refer to the Smart Note at the following link for more information. If block averaging is active, you can export blocks to ASCII. For more information, refer to the User's Manual. If you are looking to export peak and amplitude information and raw data, then you can access the IHS Peak Info utility found in the IHS Progs directory. Now, returning to the cABR FFR menu, the second option in the cABR FFR menu is the spectrogram of the response. Here, you can select to view the time-frequency distribution of the response, as well as the noise and signal-to-noise ratio. Now let's move on to the MATLAB analysis setup options. IHS offers the IHS cABR MATLAB setup utility found in the IHS Progs directory. If you have not set up this module and do not have this utility, please contact our support team for assistance. If you have MATLAB installed on your computer, you would set up by selecting the Use Install MATLAB option. If you do not have a MATLAB license and wish to use the standalone MATLAB toolbox to analyze the 170 millisecond BA, GA, and DA cABR stimuli, select the IHS standalone MATLAB toolbox setup option. If you are installing this Northwestern University MATLAB toolbox, you will also need to install the MCR and VCred files as shown on the utility. Returning to the cABR FFR menu, for users with a MATLAB license, you would use the third and fourth options on this menu to transfer data for the MATLAB Phaseogram and MATLAB pitch analysis. On the other hand, Most research audiologists do not have a MATLAB license and thus will rely on the MATLAB toolbox accessible via the MATLAB User Program Remote Program 1 option. This option will launch the toolbox. When you launch the pitch module, it will open a pitch tracking report for information on periodicity of the response. So how is this report obtained via SmartEP? Well, we start by identifying the identifier of the test subject from the patient menu, because this is a data folder where the files will be called from for analysis. Then we note the file name of the responses for which we want to do the pitch analysis. In this case, the identifier is IHS demo cABR, and the BA response is recording number 8. For the purposes of this video, I'm going to duplicate the BA recording and filter it so that we are able to get a pitch analysis for the filtered response as well. I will verify that my filter settings are set for 100 to 1500 Hz, and then activate the duplicate recording and apply the filter using the shortcut filter icon. You can see in the comments section of the new duplicate recording that the spectral filter has been applied. Save this new recording and note the recording number is 17. Now we launch the toolbox from the MATLAB User Program and select Pitch. Ensure that you are in the patient's data directory. The look-in field should match the identifier of the test subject. If you are not in the patient's directory, make sure to browse to the IHS data folder and open the data folder of interest. Then select the recording. We will start with the raw grand average BA recording number 8. The pitch tracking module will launch, and the default parameters will autofill. Then the pitch tracking report for the BA recording number 8 will be generated. Now select the Browse in the pitch tracking module and select the filtered BA recording number 17. Once the file is loaded into the module, select OK to generate the second pitch tracking report for the filtered BA. It is not necessary to do both. Both are done here for illustrative purposes. There are 3 key windows displayed in the pitch analysis: pitch track lower left, autocorrelogram with pitch track top right, and running FFT bottom right. You will also find pitch tracking measures such as pitch error, pitch strength, and cross correlation. In the pitch track plot, the black line is the pitch or fundamental periodicity of the stimulus as determined by the frequency estimation method, either autocorrelation or FFT. In this case, the stimulus was the spoken syllable ba with a flat pitch fundamental frequency of 100 Hz. The yellow boxes are the response's periodicity. The pitch error value of 0.63 indicates that on average the response differed from the stimulus pitch by less than 1 Hz. This number is an absolute value. It does not matter if the response is sharp or flat with respect to the stimulus. Correlation coefficient is the Pearson's R between the stimulus track and the response track lines. Given the nature of Pearson's correlations, the measure is most appropriate for a non-constant F0. A flat or nearly flat F0, as in this case, may result in a lower R value than one might expect given the pitch error and pitch strength. An autocorrelogram is when the signal is correlated with itself. The autocorrelogram with pitch track plots a short time running autocorrelation using a sliding window analysis. The response is chopped into 40 millisecond chunks and is successively time-shifted with a delay-lagged version of itself in 1 millisecond steps to create a 3-dimensional representation of the response signal. A Pears R is calculated at each 1 millisecond interval. The highest possible periodicity would result in an R of +1. An R of -1 indicates fully out of phase. Thus, high positive Rs indicate periodicity in the signal. Here you see time plotted on the x-axis. lag is on the y-axis, and R values is depicted by color. Lag is 1 over the frequency, or relevant to the plot, which is expressed in milliseconds, 1000 over frequency. The y-axis is inverted, 0 at the top, so that the curve of the plot matches that of the pitch track plot. The brightest colors are the highest correlations nearing 1, and appear at lags corresponding to the fundamental periodicity of the response, the same frequencies as the pitch track plot. Pitch strength is the mean of the R's at the thin black line, those of the response's pitch. The running FFT plot is the result of a short-time Fourier transfer. This is a spectrogram of the response with a thin black line signifying the stimulus pitch overlaying it. Brighter colors are higher energy in arbitrary units. The frequency axis goes up to 700 Hz in order to visualize the tracking to the harmonics of the fundamental periodicity. Next is phaseogram. This module provides an average phase shift measure within a region of interest, or ROI. In the example shown here, you can see the difference between the synthetic speech syllables ba and da. So how do you generate a phaseogram within SmartEP? I will pick up where we left off in the pitch screen capture. For the purpose of this video and for illustrative purposes, I will be duplicating the raw average GA response and filtering it so that we can obtain a phaseogram for both unfiltered and filtered responses. Once the new filtered GA response has been saved, we note the recording numbers we will be loading for the phaseogram analysis. In this example, we will compare the unfiltered BA recording number 8 to the unfiltered GA recording number 9. And then we will compare the filtered BA recording number 17 to the filtered GA recording number 19. Click on the cABR FFR menu and select the MATLAB Remote Program option to launch the toolbox caller again. Click Run Phaseogram. Next, ensure that you are in the patient directory of interest. Select recording number 8, BA, and choose Open. Then select recording number 9, GA, and this will launch the Cross-Phaseogram Analysis module. Click OK to output the graphic. The average phase shift value will appear on the top right-hand side of the graph and applies to the region of interest specified. You can analyze the default transition or consonant portion of the recording, or enter a different range and analyze the vowel steady-state portion of the result. The phase difference is plotted in radians. A positive phase difference indicates that the GA is leading the BA. Zero difference, such as in the steady-state portion of the results, means that the GA equals the BA, while the negative phase difference means that the BA leads the GA. You can switch the order plotted and view these differences. We can load different recordings to analyze directly from the analysis module. This concludes our analysis. For more information on the toolbox analysis, please refer to Northwestern University article library found within SmartEP. In conclusion, FFRs are sensitive biological markers of maturation and training of the auditory system, highly reproducible and reliable under passive conditions. It is a non-invasive, objective technique that provides important information on the biological basis of disorders of hearing and language. They provide a way to identify patients who may benefit from auditory training. In the evaluation of disorders of hearing and language, FFRs complement existing diagnostic tests such as cABR, OAE, behavioral, auditory, and speech processing tests, including speech perception test and noise. The research demonstrates how valuable FFRs are. Studies have been done to inform the potential clinical applications for FFR testing. Research implementation in clinical population by Krause et al. Have revealed a relationship between FFRs and high levels of language processing such as reading and speech perception and noise. Krause et al. Studies have shown that alterations in the FFR are strongly related to poor speech perception and noise. This was also seen in musicians who show better performance in clinical tests of speech perception and noise relative to non-musicians, with more robust FFRs to stimuli and noise. For this reason, patients who demonstrate difficulty in speech perception and noise may benefit from intervention strategies that utilize music. The FFR has also been used to assess reading ability in children. FFR studies have been conducted with populations of children who are poor readers and good readers. Findings demonstrate faster response times and more robust high-frequency spectral components in the children who are better readers. These cABR findings are possibly due to deficits in the auditory efferent pathways that prevent poor readers from establishing sound meaning relationships, which is required for reading efficiency. Anderson et al. Showed FFR fundamental frequency F0 and formant amplitude improvements in aided versus unaided individuals, thus its potential role in assessment and management of hearing impairment. Christian et al. Studied individuals fluent in tonal languages versus individuals not exposed to tonal languages in sleep and found more robust responses for tonal language individuals. This demonstrates the importance of the language experience for individuals in processing sound. Sko et al. Reported similar findings of neural responses to fundamental frequencies of vowels in bilingual versus monolinguistic children and adolescents. Cook et al. Has shown the potential utility of this type of testing for transtympanic intraoperative monitoring of mild to moderate residual low-frequency hearing preservation of cochlear implant candidates. And many are currently looking to FFR for information on neural development of speech and language, autism, and central auditory processing. Thank you for watching this video. There are 4 parts to this video series. If you wish to learn more, Part 1 covers how to acquire FFRs. Part 2 reviews complex stimuli and stimulus options. Part 3 reviews the Advanced Auditory Research Module, or ARM. For more information on the SmartEP FFR options, please contact our sales team at sales@ihsys.com or visit our website at www.ihsys.com. If you have any technical questions or suggestions, please contact our support team at support@ihsys.com.